You have been hired by Boxes R Us to design a box in the shape of a rectangular prism. This prism will hold miniature cubes. This open-top box will be made from a regular sheet of paper. Your job is to determine the size of the square that needs to be cut from each of the corners to maximize the volume of the box. So step one to a problem is to answer the question, what do we need to optimize? So we need to optimize the volume of a rectangular prism. Step two is to identify the unknowns and draw a diagram if applicable. So for step two, I've drawn here a 8.5 by 11 sheet of paper, and we need to cut out the corners. Now, to explain this further, I have a bit of a model, but before that, let's just define x, which is the second part of this step. And we're going to let x represent the side length of the rectangle to be cut out. So in terms of what this cutout is referring to, I have here an 11 by 8.5 sheet of paper, and you can see that I cut out 4 corners, and each of these corners are approximately a square that's x by x. And so when you fold up the corners, it makes a rectangular prism. So you can see that the height of the rectangular prism would then be x, and then we have an 11-inch section here, but we've cut out 2 pieces. So we've cut this piece out, and then at the bottom we've cut this piece out, and when we fold these pieces up, we end up with 11 minus 2x. And the same thing for our other dimension here. We have 8.5 by 11, so it's an 8.5 dimension. Subtract 2x because we're cutting off 1x there and 1x here to have it folded up on all sides. I hope that makes it a little bit clearer to you. So we need to optimize the volume of length times width times height, but now we have 3 variables. Obviously 3 variables are not going to help us out very much with our problem. So in this solution, I skip ahead and kind of eliminate length and width at the same time, because according to the model we just created, the length can then be 11 minus 2x, and the width can be 8.5 minus 2x. Now, I did not simplify this one in the 6th step, but you might want to simplify because, as you can see, the algebra is going to get a little bit complicated. So step 4 is to identify the constraints or the restrictions on the variables. So it's important to note that obviously if you cut too much out, you're going to go over the side of the paper. You're not going to have any base of this box left. So you have to make some sort of cut. So x has to be bigger than 0, but x has to be less than 8.5 divided by 2. And that's because obviously if you cut out too much from either side here, you're going to end up with no paper left. So we can't make a huge cut from both sides and not have any base left. So that's where I got the 8.5 over 2. So then we need to work with our volume. So I just rewrote the x in front because I find that a little bit easier. I would recommend simplifying this, but if you don't simplify this, we can use the triple product rule here in step 6 when we're going to determine our derivative. So we have the derivative of the first times the second and the third, plus the first derivative of the second, leave the third alone, plus the first and the second derivative of the third. So it gets quite long. Then we're going to let the derivative be equal to 0 and expand the whole thing out, and we end up with 12x squared minus 78x plus 93.5 as my quadratic, which makes sense because the volume equation here is a cube function, so my derivative should definitely be a quadratic. Because of the 93.5, I know that I'm going to use my quadratic formula. We're going to make sure we show our steps with the quadratic formula. So we get 1.585 approximately and 4.915 approximately. If you would like to do this using exact values, that would be great, but for the purposes of this example, I'm just going to use the approximations. And then at this point, it's always helpful to take a look back at step 4. So step 4 told us that our answer had to be between 0 and 8.5 over 2. However, 4.915 is bigger than 8.5 divided by 2. It's too much. If you cut that much paper out, there's no box left, so that's not a possible answer. So that means that our only possible answer is 1.585. So x goes from 0 in step 7 here to 1.585, and then we're looking at 1.585. We know the derivative 0, and then 1.585 to 4.25, which is 8.5 divided by 2. So I'm substituting 1 into my derivative. So into this derivative up here, I substituted the number 1 and I got a positive number. So that told me that the function is increasing. And then I substituted the number 2 into my first derivative up here and I got a negative number. So that told me that my derivative is, my function is decreasing because the derivative is negative. And then I did a quick check that if x is 0 or 4.25, my end values, the volume would be 0, which would not be maximized. So I can make my final answer. So if the cut is approximately 1.585 inches, the volume is maximized. And there's our solution.